In this video, we will be looking at right triangle application. But before we go to some examples where we take the words and turn them into right triangles and then do our trig ratios, we need to look at two key definitions. And those are the angle of elevation and the angle of depression. So for an angle of elevation, the observer is on the ground and they look up at an object in the sky. The angle of elevation is created between the horizontal and their sight line. So remember, when you're walking around, you're looking horizontally. So the motion of looking up creates this angle right here, and that is called our angle of elevation. We also have angles of depression, and those are when the observer is up higher in the sky, let's say. So here is our observer, and the angle of depression is created again with the horizontal and the sight line of looking down at an object. So if you're walking and you're looking horizontally, and then you look down at the object. So this here, between the horizontal and the sight line, is your angle of depression. A common mistake is that people put their angle of depression here. But when you walk around, you're not looking down. You're looking horizontally and then look down at your object. So don't make that mistake. Both your angle of elevation and depression are both created with a horizontal line and the sight line. So let's get started with our first example. An airplane is flying at an altitude of 6,000 meters over the ocean directly towards a coastline. At a certain time, the angle of depression to the coastline from the airplane is 14 degrees. How much farther to the nearest kilometer does the airplane have to fly before it is directly above the coastline? So first thing, I noticed that I need my distance in kilometers. So the first thing I'm going to do is just quickly turn that 6,000 meters into 6 kilometers. That way I don't forget about it. And now let's start drawing our triangle. So we have the airplane here, and let's say our coastline is here. And the airplane has to fly until it is directly above the coastline. So we need to find this distance that it is flying. We also know, now that we've created our right triangle, we also know that the altitude is 6 kilometers, and the altitude is just the distance the airplane is above the ground. So we can label this the altitude, because the altitude won't change if it's just flying horizontally. And then we know that our angle of depression is 14 degrees. So we have our horizontal line here, and if our airplane were to look down to the coastline, that would be our sight line. So this right here is 14 degrees. Now we have a right triangle, we have an angle, we have a side length, and we're looking for a missing side length. So whenever we're given our angle, this will be our reference angle. And like always, let's label opposite, adjacent, and hypotenuse. And in this scenario, we're given opposite and we want adjacent, which means we will use our tan ratio. So tan 14 is equal to the opposite side, which is 6, over the adjacent, which is x. And just as a reminder, whenever you're looking for a side length, you're going to put the sine tan cos over 1 and then cross multiply. And when we cross multiply, we will do x times tan 14, and that's equal to 1 times 6. And in this scenario, because x is not isolated, we will have to divide both sides by tan 14. And when we do that, we're going to get approximately 24 kilometers. Now I didn't put any decimals because it said to round to the nearest kilometer, so no decimals were needed. So now we can write our therefore statement. Therefore, the airplane must fly 24 kilometers to be directly above the coastline. And that's it. So we took our words, we created a right triangle, labeled everything properly. We were careful with the definition of an angle of depression, And then it was back to our knowledge of SOHCAHTOA. So let's try the next one. All right, a ladder leans against a building. The foot of the ladder is 6 feet from the building. The ladder reaches a height of 14 feet on the building. Determine to the nearest degree the angle the ladder makes with the ground. All right, so in our diagram, I have a building, and I have the ground, and I have a ladder. So this is our right triangle here. So the foot of the ladder is 6 feet from the building. So this is the base of the ladder, and here's the building. So this would be 6 feet. And the ladder reaches a height of 14 feet on the building. So if this is my ladder here, it hits the building here. So this must be 14 feet. And now I need the angle the ladder makes with the ground. Since the ground is the base, this is the angle I'm looking for, and I will label it X. So now that we have our diagram, I'm looking for an angle. So that will be my reference. And then 14 is opposite, 6 is adjacent, and my blank side is the hypotenuse. So once again, we have opposite and adjacent for our ratio, so we will use tan. So we have tan x equals opposite 14 over adjacent 6. And as a reminder, when you're solving for an angle, you will always be using the inverse of tan in this scenario. So we will have tan inverse of 14 over 6. And when you put that into your calculator, you get approximately 67 degrees. And it says to round to the nearest degree, so again, I don't need any decimals. But now, because it is a word problem, I have to remember my therefore statement. So therefore, the ladder makes an angle of 67 degrees with the ground. And that's it for this one. All right, let's try one more. So Sandra is standing 80 meters away from a flagpole. The angle of elevation to the top of the flagpole is 18 degrees. If Sandra is 165 centimeters tall, calculate the height of the flagpole to the nearest hundredth of a meter. So 100th of a meter just means 2 decimals. So what I want you to do is pause the video and try to set up your triangle. And for now, I just want you to ignore Sandra's height. Just draw a right triangle where Sandra is standing 80 meters away and her angle of elevation is 18 degrees. Once you've done that, come back to the video to check your work, and then we'll deal with Sandra's height. All right, so when you're drawing this, here's the flagpole, let's say. And Sandra's here on the ground. She's 80 meters away, and her angle of elevation is 18 degrees. So hopefully you have this. But now, Sandra's eyes are obviously not on the ground. So this point here where the 18 degrees is, that's her eye level. So her height of 165 centimeters, we have to place it right here as a little add-on to the height of the flagpole. So first of all, I'm not going to put 165 because my other units are in meters. So 165 centimeters is 1.65 meters. So now I will solve in my right triangle. So right here, I will solve for that side length and I'll label it X. But then the actual height of my flagpole, we're going to have to add on her height, because that angle of elevation isn't starting from ground level, it's starting a little bit higher. So let's go ahead. Now that we have our diagram, 18 is my reference angle, X is opposite, 80 is adjacent, and the blank side is hypotenuse. So once again, we are looking for opposite and we're given adjacent, so we will be using tan once more. So I want you to pause the video and try to finish this question on your own. So solve for X, and once you have X, add on that 1.65, and remember, round to 2 decimal places. All right, so when you set up your tan ratio, we should have tan 18 equals x over 80. When you cross multiply, you're multiplying 80 with tan 18 to give you 26.00 meters. I added the 00 just because I need that rounding to the nearest hundredth. And then I have to remember to add Sandra's height. So the flagpole ends up being 27.65 meters tall. And that's it for application. So the actual knowledge part of setting up your ratios, solving for sides or angles is the same. You just have to be able to take the words and turn them into the right triangle. And sometimes you have to be careful to consider an extra height to add on later on. Just make sure you don't overthink it and think that there's only a triangle in your scenario when sometimes there's just that little extension piece, like in example 3. But for the most part, it's usually just a simple right triangle like we have here in example 1 and 2.